Stack Overflow.
It's a phrase that has probably saved your career a dozen times. Right?
Oh, at least. I mean, probably once a week. If you're in tech, or even if you just, dabble in coding, Stack Overflow is the holy site.
Mm-hmm.
It's where you go when you're desperate. You've got a deadline, your code is broken, there are 5 error messages you don't understand.
And you just want to copy-paste a solution from a stranger on the internet that actually works.
Exactly. It's the savior of deadlines everywhere.
It is. It's a vital resource. But today, we're not talking about the website.
Right. We're talking about the reason the website has that name in the first place.
We are.
We're talking about the actual technical catastrophic event, a buffer overrun in the stack segment.
Which is infinitely more dangerous than just having a bug in your code. We're diving into a set of technical notes called Stack Overflow Memory Corruption.md. And the mission for this deep dive is pretty specific. We want to move past the idea that bugs just, make programs crash. We want to understand how a hacker can physically overwrite data in a computer's memory.
To trick a program into doing something it was never, ever designed to do.
Precisely.
I love this. So we're not just breaking the machine, we're puppeteering it.
Exactly. We're going to look at the physics of memory corruption.
I like that framing the physics of it, because usually code feels so abstract to me. It's just text on a screen, right? Logic floating in the cloud.
You're saying this is about physical space.
Well, yeah, is it?
It is entirely about space and capacity and limits.
Okay.
When you get down to the metal, variables aren't just abstract ideas. They're data sitting in physical slots on a silicon chip.
Okay.
And if you try to put too much into one of those slots, well, physics takes over. It has to go somewhere.
So before we start smashing things and stealing data, let's unpack the stakes. Why should we care about a Stack Overflow? Is it just that the program stops working?
It's much, much worse than that. To really get the stakes, we have to look at something called the CIA triad.
Okay, CIA. And I'm assuming we're not talking about spies in trench coats here.
Not quite, though the stakes can be just as high. In information security, CIA stands for confidentiality, integrity, and availability.
The 3 pillars of a secure system.
Exactly. And a Stack Overflow has this unique, terrifying ability to violate all 3 of them at the same time.
Wow, a clean sweep. Let's break those down. Availability seems pretty obvious. If I crash your computer, it's not available.
Right, that's the most basic consequence. You cause a segmentation fault, the program dies, and boom, you've killed availability.
Okay.
Then there's confidentiality. In a worst-case scenario, a Stack Overflow leads to something called remote code execution, or RCE.
RCE. Yeah, that's the big one.
That is the nightmare scenario. It's where an attacker uses the overflow to run their own code on your machine. They can read your files, steal your passwords.
Open your webcam.
They have total control. So confidentiality is just gone.
Which is basically game over.
It is. But for this specific deep dive, based on the notes we have, we're going to zoom in on the I in CIA. Integrity.
Integrity. So in the real world, integrity means doing the right thing when no one is looking. What does it mean for a computer program?
It means the data is trustworthy. It means that if a variable says user is admin, false, then that data hasn't been tampered with. It reflects reality.
And we're going to see how a Stack Overflow lets you just overwrite variables with whatever data you want.
You're changing the program's reality from the inside out.
So you aren't just breaking the lock, you're changing the shape of the key.
Or you're convincing the door that it was never locked to begin with. You aren't just breaking the machine, you're lying to it. And because of how memory is structured, it has no choice but to believe you.
That sounds incredibly manipulative. I'm ready. So how does this mechanism actually work? The source material calls it memory corruption.
Right, and memory corruption isn't random. It's not just, throwing a wrench in the gears and hoping for a spark. It's about precision.
Okay, give me a concrete example. The notes mention a specific scenario with a variable called num.
Right, let's visualize this. I want you to imagine the computer's memory, specifically the stack, as a very strict, organized shelf.
Okay.
And inside a program, you define a buffer. Let's call it a buffer 2.
And a buffer is just a container, right?
Think of it like a bucket. It's reserved space meant to hold a specific amount of, say, water, or in this case, characters of text.
Got it.
Now, sitting right next to that bucket on the shelf is a little piece of paper with a number written on it. That's our variable, num.
Okay, I've got the visual. Bucket on the left, piece of paper with a number on the right.
Perfect. Now, the goal in this demo is to overwrite that num variable with the string BCDE.
Wait, pause. Num is a number variable. B, C, D, E are letters. How? How does that work?
That's the beauty of memory corruption. To you and me, they're letters. To the computer, everything is just bytes, ones and zeros. BCDE has a numerical value.
So if you shove BCDE into the space where the number is supposed to be,
The computer will just try to interpret those letters as a number.
it just does what it's told.
Precisely. But the trick is, how do you get BCDE into the num spot? You don't have direct access to write on that paper. You only have access to pour things into buffer 2.
I see where this is going. I pour too much into the bucket, and it spills over onto the paper.
That is exactly it. But you can't just pour blindly. You need to know the offset,
The offset.
the distance. You need to know exactly how many drops of water, how many bytes num is away from the start of buffer 2.
So you have to find the difference between the memory addresses.
It's a spatial puzzle. If you pour too little, you just fill the bucket. Nothing happens. If you pour way too much, you might overshoot num entirely and overwrite something else, which usually just crashes the program.
You need to fill the buffer exactly to the brim and then spill just enough to cover num.
Exactly.
Yeah.
So hacking, in this case, isn't about typing fast in a hoodie. It's about measuring distance.
And there's a technical nuance here that the source highlights, which is critical if you're doing this on 86 architecture.
Here's where it gets really interesting. The notes mention something called Little Endian.
Yes. Recall by 86 stores integers in Little Endian. That's a direct quote.
I feel like I should know what that means. It sounds like something from Gulliver's Travels.
It actually is from Gulliver's Travels. Swift wrote about wars over which end of the egg to break, but in computing, it refers to the order in which bytes are stored.
Okay.
In Little Endian format, the least significant byte is stored at the smallest address.
Okay. Translate that for me. What does that mean for my spell?
Put simply, it's like writing a number backwards in memory.
Backwards.
So let's say you want to write the number 0 by 1, 2, 3, 4. In Big Endian, which is how humans read, you'd write 12, then 34. But in Little Endian, the computer stores it as 34, then 12.
That seems confusing. Why would it do that?
Oh.
It's an efficiency thing for the processor's circuitry. But for you, the hacker, it matters immensely. If you want to overwrite num with a specific value, you can't just write the data in the order you read it,
You have to craft your overflow string in reverse byte order.
so that when it lands on the stack, it reassembles into the number you actually wanted.
So if I don't account for Little Endian, my hack just fails.
Your hack works in the sense that you overwrite the memory, but you'll overwrite it with garbage instead of the specific value you needed. You'll just scramble the data rather than control it.
This really highlights that we're visualizing this stack of main. We have our variables pushed onto this stack.
Right. When the program starts, it reserves this stack memory. The key question for a hacker is always, what's the order? When you take user input and copy it into a buffer, what happens to its neighbors?
It's a bad neighborhood to live in if you're a variable sitting next to an insecure buffer.
It really is. The source explicitly asks, when argv1 is copied to buffer 2, what may happen to other variables? And the answer is memory corruption.
Right.
It's a physical spatial issue. And languages like C and C++ just assume you know what you're doing. They don't check the bucket size for you. They just say, you want to pour a gallon into this pint glass? Sure thing.
And that spill changes the data next door. That's the integrity violation.
Precisely.
Okay, overwriting a random number is cool, but the notes talk about something way more cinematic, changing the flow of program execution. This feels like the magic trick portion of the show.
This is where we graduate from vandalism to actual hacking.
Okay.
You're going to look at a demo program from the source called authenticate.cpp.
Authenticate.cpp sounds like a password checker.
That's exactly what it is. It's a simple program. You get the password right, it grants access. You get it wrong, it denies you. Standard stuff.
But according to the source, there's a way to get in without knowing the password at all.
There is, and it involves the letter A.
Specifically, 17 of them.
Right. The exploit is simple. You run the program, and when it asks for the password, you just type in 17 A's. A, and so on.
And the result.
Access. Granted. You're in.
Okay, that is wild. I type a bunch of gibberish and the security system just folds. Why does 17 A's work? Why not 16? Why not open sesame?
It all comes back to the stack layout. In the check authentication function, there are two key variables sitting on the stack. First, a password buffer.
That's our bucket.
Right. And sitting right next to it at a higher memory address is an integer variable called auth flag.
Auth flag. Let me guess. That's the variable that decides if I'm allowed in or not.
Correct. In the code, auth flag starts at 0. In C++, 0 means false.
So access denied.
Right. If you type the correct password, the program would manually change that flag to 1 or true.
But we aren't typing the correct password. We're typing 17 A's.
Right. And here's the math. The password buffer is exactly 16 bytes long. When you type 16 A's, you fill the bucket perfectly.
Okay, so far so good.
But you type 17. That 17th A has to go somewhere. Since authflag is sitting right next door, that A gets written directly into the memory space of authflag.
So authflag is no longer 0, it's A.
Exactly. And here's the logic loophole. In C++A, any integer value other than 0 is treated as true.
Oh, wow.
The letter A has a numerical value. Its ASCII code is 65. So suddenly authflag is 65. The computer looks at that, sees a non-zero number, and says, oh, this is true, access granted.
That is hilarious. The computer thinks it's checking a sophisticated security flag, but it's actually just checking a piece of the password that spilled over the edge.
It violates the integrity of the program itself.
Yeah.
The program logic is sound, but the data it relies on has been corrupted underneath it.
So we have this theory, 17 A's, spills over and hits the flag, but how do we prove it? The source goes into some detail about looking under the hood.
This is the investigation phase. The source introduces two critical tools, GDB and PETA.
GDB is the GNU debugger. What's PETA?
PETA stands for Python Exploit Development Assistance. It's basically a plugin for GDB that makes it way easier to visualize what's happening in memory. It adds color, shows the stack, it makes the invisible visible.
So we're essentially freezing time inside the computer to catch it red-handed.
Exactly. The process in the notes is really a step-by-step forensic analysis. First, you load authenticate.exe into GDB. Then, you set a breakpoint at the check authentication function.
A breakpoint basically tells the computer, run until you get here, then freeze.
Right. So you run the program with the 17 A's argument. The program starts, takes your input, then pauses.
Right.
Then you step through the code line by line until you get just past the strucky command.
The string copy, that's the moment the spill happens.
That's the moment. And PETA shows us the memory addresses. It's like a map of the neighborhood. We can see the password buffer and the auth flag.
And their relative positions. The source mentions checking the addresses.
Yes. It says address of auth flag is at a higher address compared to the address of password buffer. This is vital. For this to work, the flag has to be above the buffer.
And we can prove that with math.
Simple subtraction. You subtract the address of the buffer from the address of the flag. If the result is positive, the flag is at a larger address. It confirms that the overflow will flow up into the flag.
And in the GDB view, you can literally see the value of auth flag change.
You can. Before the copy, you see 0x00. After the copy, you see 0x41. That's hex for 65. That's our A.
That's the smoking gun. You have physical evidence that the 17 A's overwrote the decision-making variable.
Exactly.
Okay, so looking at this, I see a logical solution. If the problem is that the flag is sitting next to the buffer, why don't we just move the flag?
That is the what-if scenario.
No.
It seems like common sense, right?
Yeah.
If auth flag gets overwritten because it's a neighbor, let's just move it to a different neighborhood.
Yeah. In the code, just declare the auth flag variable before the buffer. If variables are pushed onto the stack in order, changing the order in the code should change the order in memory.
Right.
That's the theory. The last variable declared is typically pushed last, ending up at the top of the stack.
So we have a second demo program, authenticate2.cpp, where they do that.
Right.
They switch the order.
Right. The logic is, if auth flag is at a lower address than the buffer, and buffers fill upwards, you shouldn't be able to overwrite the flag. The spill would go the other way.
So, does it work?
Well, here comes the twist. The source reveals a harsh reality. Can you still overflow if the variable declaration orders are switched? The answer is often yes.
Wait, why? If I moved it, I moved it?
You moved it in the source code, but you don't decide how the memory is arranged on the chip. The compiler does.
The compiler. The thing that turns my code into the program.
Yes. Compilers are smart. They try to optimize things for speed or space. And the source notes state, one plausible explanation is compiler optimization. So the compiler might literally undo my security fix because it thinks it knows better.
Essentially, yes.
Yes.
It might look at your code and say, I know you wrote it this way, but for memory alignment reasons, it's more efficient for me to arrange the variables this way.
That is incredibly frustrating. You're fighting the tool that's supposed to be helping you.
It is. But it gets worse.
How can it get worse?
Let's say you succeed. Let's say you turn off optimization, the compiler listens, and auth flag is safely tucked away at a lower address. You can't overwrite it. You're safe, right?
I would hope so. I moved the target out of range.
Wrong. Because remember, you can keep writing. If you pour enough water into that bucket,
Yeah.
you overflow the buffer, you miss the flag because you moved it,
Yeah.
but you keep going up the stack. What's sitting above all the local variables?
I don't know. What?
The return address.
The return address. Break that down for me.
Every function needs to know where to go back to when it's finished. If main calls check authentication, the computer leaves a breadcrumb and address, so it knows where to return. That address is stored on the stack.
Oh, I see. So if I keep writing A's, eventually I'll flood the buffer, miss the flag, but keep going until I hit that return address.
Exactly. And the source makes a chilling point here. If off flag is in a lower address, you can still overwrite other parts of the memory, including the caller's return address.
And if I overwrite the return address, what happens?
You aren't just tricking the password check anymore. You are hijacking the entire program. When the function trying to return, it goes to the address you wrote there.
And if you point it to malicious code, that's remote code execution.
That's RCE.
So simply moving the variable is like rearranging deck chairs on the Titanic. The iceberg is the stack architecture itself.
It is. And the source notes end this section with a very ominous, almost cheerful sentiment. It says, great, let's keep going.
The smiley face really drives the point home.
It does. It implies this isn't a bug, it's a playground. The unfixable nature of this, just by shuffling code, is the key takeaway.
So let's recap this journey. We started with the basic concept, Stack Overflow, not just a website, but a physical violation of memory space.
We saw how it violates the CIA triad, specifically integrity. We looked at the mechanism, offsets, little Indian architecture, and the spatial reality of the stack.
Then we did the magic trick with authenticate.cpp, 17 A's to bypass a password.
And we validated it all with GDB and PETA. We froze time, looked at the addresses, and saw the smoking gun evidence of the overwrite.
And finally, we tried to fix it by moving the variables, only to learn that the compiler might betray us, and even if it doesn't, the return address is still sitting there, waiting.
It really highlights the fragility of programs that rely on variable data on the stack. It's a fundamental issue of how computers store and retrieve temporary data.
It's a sobering thought. We trust these machines to be logical fortresses, but underneath, they're just buckets of bytes, and if you spill over the edge, chaos ensues.
Chaos or opportunity, depending on which side of the keyboard you're sitting on.
That is a fascinating place to leave it. So, to the listener, next time you see a password field, you might just wonder, what happens if I type 5,000 characters instead of 5?
But please, don't actually do that on a system you don't own. That is illegal.
Right. Stick to your own local host. Thanks for diving in with us.
Great. Let's keep going.